Okay, so according to the problem description, I sketched out a high-level view of the system right here. Overall, the client will interact with the storage server through a directory microservice. This directory, as a coordinator, will forward the requests from the client to the corresponding buckets um, uh, based on the output of this hash function. Inside the bucket, I implemented a custom storage engine which reads and writes data to a custom file structure. Um, the communication between these microservices is HTTP, but I'm calling HTTP in the RPC style, not RESTful. The function the hash function I use for directory is called jump consistent hash. It's quite popular in the distributed system world um, for the minimal output changes when number of buckets change. It is described right here in this paper I linked. The implementation code was written in C++, but I just had to uh, translate this into JavaScript, and yeah, that's all about it. For the buckets, I implemented a append-only log kind of file. So I'm storing operation type, key length, value length, and the content of the key and the value. So this is how it looks like after one insert, and this is how it looks like after one delete. It's really capacity efficient. And once a bucket service started, it will read the entire file and store the content into a map data structure in memory. This is efficient for search and range. I mean, they're literally the same operation. Okay, in the regard of CAP theorem, my system guarantees consistency because there's only one entrance, which is the directory API, and the buckets store data in only one place. So literally everyone sees the same data at the same time. However, it does not warranty availability because it's quite predictable that I am developing the system and deploying the system on a single node. So any outage will just break the availability. And about partition tolerance, again, because there's no replication of service, just any network partition between directory and buckets which make them not able to find each other will affect the data availability, and so but it actually can be solved by adding replications, at least with Kubernetes. Okay, about the client report. As you can see, that data was sent to all the buckets available. And here is the file size after saving data. Yeah, everything is accessed properly. Yeah, everything functions according to expectations. So, yeah. And inside this test client, I separate into each steps. Separate script into each steps here. There is a limit. I put a limit kind of thing in the insert step because the file is quite large and reading the file too fast will just push too much requests onto the servers, and it causes a strain there. And additionally, I deployed an Nginx as a reverse proxy to queues up the requests to further reduce the strain on the server. Yeah, it's just a problem with local deployment. But actually, a cloud deployment would require a kind of API gateway anyway. But yep, that's it. I think the next step is to show how to actually run this project. I made a Docker compose file to ease out the setup. The only thing you have to do is to build the images, build 3 images, and then run the compose server up. Yeah, I built previously, so I'm not going to do it again, but the compose server up. Once they start it up like this, you will want to run the discovery info to make sure that all 3 buckets are registered on the directory, and you can start experimenting data. Let's see, range data, change the keys. So there are 2 entries. Increasing the range will result in 3 entries. So that's it. And for the client, you can also just run compose, this command, to fire up the client, but I'm going to run it locally. But let's try to run this on a smaller file instead of 88 megabytes file. Yep, that's it.